It's a pleasure to be here at JupyterCon. Just as a side note, it's been really fun to see JupyterCon develop over the past, year and a half. We started talking about this, I guess, about a year and a half ago, and or maybe a little bit more, but like some of the Jupyter Day events, we were kind of envisioning having a conference, and now seeing how it's turned out and the keynotes and everything, it's just fantastic. Alrighty, so humans in the loop. This is about a kind of design pattern that's emerging and in ways of getting people and machines working together for AI apps. We're using this at OReilly. Some of our team is over here, and Taylor Martin is on our team. She just told me this was perfect setup to have some kind of a human in a habit trail ILO. I think I'll have to do that for the next slide. So a little bit of framing. If you could imagine having an mostly automated system, so people and machines collaborating together. And even though it sounds a bit sci-fi, there's a lot of this. I mean, if you have an e-commerce site and it's running at scale, but then you've got customer support, to some extent, you've got people and machines working together. The challenge is, can we go beyond that? Can we have something that's more advanced, where computers are not just running code libraries, but they're actually doing fairly difficult decisions. They're exercising some kind of judgment. They're working with complexity. And even better beyond that, can we have systems where the machines are being trained by human experts, not because of the code that's being written or the model parameters, but really just by being shown examples pro and con over and over. So the scope of this then is to try to bring people and machines together in workflows, working on relatively complex problems, and training by examples or exemplars. And anybody recognize the illustration there? It's a little bit of deep learning in practice. It's Deep Dream Generator, but it's, there's a guy, I believe, lives here in New York City who had an antenna installed and has been filing for legal classification as a cyborg. So some of the research questions, and it really got into trouble with TSA too, by the way, but some research questions then. We're working at OReilly. We do conferences. We have a learning platform called Safari, and our team, learning group here, we're really focused on personalized learning and how can we put together the building blocks for a personalized learning kind of platform. And with that, OReilly is much about peer teaching. Ever since our founders were classics majors at Harvard back in the 70s and wound up at a Unix user group meeting in Boston and recognized just how horrible the man pages were, and decided that they actually knew how to write. You know, probably they could contribute as writers, given that they were fuzzy studies majors and they like to write. And so they've been very interested in peer teaching across different kinds of mediums. So, you know, we did books for a while, we did conferences, and we've done other types of media formats, and every time we try to bring back that sort of peer teaching perspective. So how do we help the experts, who by definition are really busy, be able to engage and share what they know in conferences like this? We also have a challenge in terms of editors, and I'll really dig into this, but the kinds of media that are evolving are not as friendly to editors as they could be. So how do we try to keep that role of being an editor, being really effective, more at a human scale? And so to illustrate some of this is a prototype for like a next generation of search that hopefully will be coming out pretty soon for OReilly. And you know, you can see you've got a little bit of navigation on the side there that shows you topics. You can navigate topics and similar searches and all. The point being, though, is that part of this content is generated and curated by humans, and part of it is generated and curated by applications from AI. So here, what you're seeing on the page, there's some extractive summarization that's done in machine learning. Certainly, there's a lot of work in terms of ontology and then semantic search in terms of the indexing. There's various cases for deep learning that are applied here, and we'll go through some of those. So in terms of machines learning, I want to kind of cover this a bit. You probably hear in machine learning, I guess everybody here heard of supervised learning. This, okay? So you've got a data set, and every row has a label, and you can build up learners. You can optimize a set of learners so that they can predict labels given the data. Typically, you're doing some kind of holdout to train on a portion of a data set and then test on the remainder. Deep learning, basically structured layers of neural networks. It's become a very popular way of an example of supervised learning. But one of the problems with deep learning is that unless you have a lot of carefully labeled data, it doesn't really apply. I teach courses that use deep learning for natural language processing, and even with the toy examples, until you have at least like 10,000 examples to train on, the results are horrible. It's more like until you get into the millions that you start to get some convergence and some better examples. And so that's in category for us, because when you look at chapters and segments of videos, we have millions and millions of those. But that's a caveat, that deep learning is very popular now, but it doesn't necessarily apply unless you have labeled data. And as it turned out, in a lot of cases, we don't. Unsupervised learning is another popular form that people talk about. And that's where typically you're doing some kind of high-dimensional data and then some sort of low-dimensional embedded structure. Things like k-means or other clustering algorithms are very popular examples of this. Neural networks without the deep structure component are typically unsupervised learning. And you don't have the labels. You don't need them. But on the other hand, you kind of have to dig into the structure that you get to figure out what it really means. So it's still an open question how much that contributes to AI. But there's something else that doesn't get talked about as much. It's called semisupervised learning. And we're going to focus on a special case of this called active learning. And the idea is that if you have a machine learning, let's say you have an ensemble of machine learning models that can predict some type of outcome, some type of label. If the ensemble can agree on making a prediction, great, take it. It's automated. But if the ensemble disagrees or has very low confidence in what it's trying to produce, then take that sort of edge case and kick it back to an expert. And so this way you can have it work mostly automated, but when you run into an edge case where the machines really can't agree on it, then kick it back to an expert, and what the judgment that the expert makes, that iterates into training the model. So now if you can train a model based on examples, you have a pretty nice workflow, a pretty nice pipeline for putting together humans and machines. And a nice thing about this is that it works really well if you have a lot of data that isn't labeled, and where really the problem is getting to the labeled data set. So as a case in point, there's a company in San Francisco called CrowdFlower. They've done some nice talks and case studies at OReilly conferences. You know, Google, when they started doing self-driving cars, they had a lot of really complex models, machine learning models for the different activities in a self-driving car. And they'd gotten down the road some success with self-driving cars, and then they started applying very sophisticated deep learning models that just wiped out those models. The prior work of machine learning was subsumed by a lot more work with deep learning. And the moral of the story there is that Google has had years of collecting carefully labeled data sets at scale about driving. And so now the auto manufacturers out of Detroit are suddenly showing up in San Francisco with big piles of unlabeled data saying, oh yeah, we need that too, and here's a big pile of money. Do something. Active learning is a way that, for instance, the auto manufacturers are getting those labeled data sets. But it's used in a lot of other areas as well. So here's a book that describes, actually it's an article, but there's also a downloadable book for it too. Tecuzio talking about active learning, really kind of breaking it down, using CrowdFlower as one of the case studies. And down here too, one of the parts out of the book was what kind of policies. You're going to have bias in the system, so where do you tilt the bias toward to make it most optimal? And I'll talk about how we use that a little bit later. CrowdFlower, Luke Biewald is a person who created that, and pretty popular kind of overlay on top of mTurk is a way of thinking about it. So if you're familiar with the mTurk mechanical Turk service out of AWS, then CrowdFlower is like another layer that can add some quality and statistical measurement of results of the mTurk's output. And it's a nice kind of overlay for integrating active learning into that crowdsourced problem. Another really great example of it is Stitch Fix. Any customers of Stitch Fix in the audience? or spouses of customers. Yes, that too. Or it's probably more where I fit in. But they have some great talks and case studies about this because they do combine a lot of human expertise along with machine learning. And so, a case in point there, Eric Colson was talking about, they can do excellent things for fashion selection with machine learning. But the machine learning models have no idea how the people feel about it. And so you really need to introduce that kind of human component to have that kind of emotional connection with what the product's supposed to do. So very interesting ways of combining people and machines. Another one which I think is increasingly sophisticated, Jason Laska gave a talk here at the AI conference, actually not this room, but the next room, about 2 months ago. And great case study. Essentially, it's like a two-sided marketplace. And so there are jobs that need to get done. If they can be performed entirely through automation, through some kind of AI process, then the amount of spend to get the job done goes down. If it's a job that requires a person to do, then the cost is higher. And so effectively, the people doing these tasks, if they can't outperform the machines, they aren't going to make as much money. But if they want to level up and earn more money per job, then they can start to find out areas where a human can outperform the machine. And so it's interesting because you end up with a kind of spectrum of what is it that people do well and what is it that machines do well, and starting to quantify that and show market dynamics, elasticity into that. So I think it's a really great what Clara Labs has been publishing about what they're doing. And kind of a flip side for that too is Adam Marcus from B12 here in New York City, where they're using AI to build out business websites. And so they're able to use automated systems to build out most of what a customer needs, and then kind of at the last mile, web developers get involved. They've created an open source project called Orchestra to help with some of their active learning work. Along with that, the person behind that, there was Adam Marcus, and he talks about another project here called Flash Teams. Anybody run across Flash Teams yet? It's sort of like Uber for crowdsourcing. No, that doesn't sound right. It's sort of like something above crowdsourcing, above Mechanical Turk. And as I understand, this is out of Stanford. I've talked with people at Accenture who are helping to fund this research at Stanford HCI. And the idea is, Accenture is a consulting company. They send teams into enterprise to do jobs. They want to understand how to put together ad hoc teams on the fly, basically crowdsourcing their workforce to some extent. Find out who are the people who work well on a team in an enterprise setup for a given kind of problem. And so what's going on with Flash Teams then is sort of, it dovetails very nicely with active learning, and B12 is an example of where they're trying to put these two together. One other thing I'll show, this also falls under the category of human in the loop. Whereas I've been talking about active learning as a design pattern called human in the loop, there's something out of Stanford. Alex Ratner here is one of the grad students working on the project. It was originally called Deep Dive, and then a subsequent version of it is called Snorkel. And the idea is they're using an approach called weak supervision. So in contrast to the semi-supervised that we were talking about, or unsupervised or supervised learning, weak supervision is applying an approach they call data programming, essentially building up functions to feed in data that's trusted more or less to develop the features. So really, instead of putting a lot of work toward the feature engineering, let's back up and start engineering the supply of data. And we know that in certain cases, some data sources are more trusted than others. So how can we actually move the learning back up to that stage? And it's another fascinating example of human in the loop. We're actually looking at trying to apply this at OReilly. And then reinforcement learning. We're not using this yet, but it's another kind of contrast to these areas of learning. And I used to work on Spark out of Databricks, very closely associated with UC Berkeley EECS. And my former boss left Databricks. He's gone back to lead a project called Rise Lab at Berkeley. And they're just putting all the chips in toward reinforcement learning. They feel this will be the next big wave for what's going on in AI. Okay, so that gives some context then of different ways of getting people and machines to work together. But I really want to focus on the active learning part. And I want to give a little bit of context about what we're trying to solve with our team and how we ran into this problem. So we're working with AI in media. And the idea, simply put, is that if you've got some kind of content that can be represented as text, then of course you can go in and use NLP to parse the text. Once you've got it parsed, you can do a lot of fun things with it, whether it's summarization or semantic similarity or some type of named entity extraction. There's just a lot of things you can do once you've got a parsed text. Of course, if you've got audio or video, now you can get it transcribed. And so, for instance, you could do AI services in the cloud to get transcriptions out of video and now start to apply a lot of these techniques even in another media format. So there's a lot that we can do building off of NLP. And if you have images, you have large sets of labeled images, such as we have coming out of a conference with all the slides and the video, that gets really interesting too. And we presuppose that this kind of content, when we apply machine learning to it, we're presupposing there's some sort of structure there. There's some kind of low-order embedding, if you will. And there is, we hope. We hope that the learning materials are teaching something, so there's some kind of structure. But representing that kind of structure is fairly rare in media. So we're trying to work on this. We're trying to find others who are working on it as well, of really how to do the representation part. So as an example, here's a popular instructional video that we have, Intro to Docker by Andrew Baker. And up in the top left, there's a transcript that came out of a cloud service using AI to transcribe from an MPEG into a snippet of a transcribed utterance, if you will. And then on the right-hand side, we've got the results of parsing, running this through Spacy and in Python and also TextRank. And then from there, being able to extract out what are key phrases that are important out of that chapter of video, that segment of video. And you can see Andrew Baker was giving some setup for Docker, and he was contrasting it with earlier technologies like VMware. So section 1 of his video was about the previous kind of virtualization strategies. And you can see what pops out is virtualization tool, VMware hypervisor, VirtualBox, the things that came before Docker. And then over on the left-hand side, there's some tie-in to part of our ontology. And then by using vector embedding, deep learning, we're able to go and expand that to take a look and see, well, as it turns out, machine learning tells us that here Docker and Docker container tend to be associated with things like CoreOS and Kubernetes and Mesos and OpenStack, sort of in that realm of DevOps, the devil you know. So these are ways that machine learning can be used with learning content in media. Now, getting back to the humans in the loop, part of the problem is that we've got a whole bunch of data products, if you will, that are machine generated, that come out of machine learning. But we want to be able to have some kind of control points for that, basically ways to steer the ship. So we have an ontology that's really more on the order of a few hundred rules. And then we have the machine learning products output, which tie into it, which are on the order of billions of data points. So you can think of having an ontology as a kind of graph at a human scale. People can work with it. It's the primary structure of what we're working with. It's sort of the control points for a lot of this automation. It's also a matter of what can we test and verify, validate. But then you've got this small graph that's basically tracking a much larger graph below it. And so the game is to try to keep some structural correspondence between those two. And then the big win for us is to have a nice, large annotated graph and do inference across it. That's where the AI part of this really comes in. So ontology is something that deep learning doesn't give you. It really helps provide a lot of the context. And so you've probably everybody here heard of Knowledge Graph, Google project, College Knowledge Graph, a very famous project in ontology. Essentially what you're doing is building a computable thesaurus, and it's typically represented as a graph. So graph algorithms work out really well. In another way, you can think of it as like the semantics of business relationships. And that's what we're doing, is mapping out all the business relationships across OReilly and our partners, and what do they mean in a given context. So I mean, just an example, here's a visualization out of D3 for part of our ontology, and this was the part that was linking back in. It was referencing Library of Congress, their catalog for how do we link in through OCLC, MARC records, et cetera. And then it's also linking into DBpedia, which has some structured data about deep learning. So it's great, because if you can put that kind of structure on your content, you have those labels and you can link in at the right place, then you can go and access resources out of places like Library of Congress or DBpedia. You can really make a lot more use of it. But there's a problem. So disambiguating context is hard, and it's not something that that deep learning is going to solve anytime soon, apparently. It's not something that ontology really solves. It's not really something that there's a lot of tooling around yet. So when you have overlapping contexts, it really gives you a hard problem in any kind of natural language understanding. There's not a lot of tooling, and it also, the whole thing sort of runs counter to this big wave of correlation that you see in big data, right? We're looking for patterns, and if the patterns all can be generalized, great. And then we find out that that's actually the problem that's biting us, is that having too much correlation is a bad thing. And just for kicks, I did some correlation here between Firefly and The Expanse. So I don't know, that's just my view of the world, but we'll see. Correlation and not causation. So the problem we have is, suppose somebody publishes a book and they use the term iOS, and they're talking about an operating system. So are they talking, based on that a priori knowledge, are they talking about an iPhone, or are they talking about a Cisco router? Because it could be either. And we have a lot of content about both. And if you want to do personalized learning, you have to be able to disambiguate those contexts. And if you have enough signal on a person, yeah, you can use that as a prior. But when they first start out and they first have initial experiences, you want those to be good UX experiences. You don't have data on them. And so there's kind of a chicken and egg problem there. This would be great to use deep learning on, if we could, except for, by definition, we don't have labeled data. So we can't really train. We have to bootstrap that. So just an example, if I were to search for React on Google, my first page of results comes back with things about charities and surveys and video games and, oh yeah, UI web components. Now, with our audience, if I say React, well, naturally, what you're talking about is business leadership. When you're conducting interviews or doing a sales meeting, how do people react? Because we have a lot of content about that, and that's super important. But obviously, if you're talking about React, what that means is some ions are interacting because there's a chemistry balance, and so you've got things like valence and whatnot that are going on, because that's really important for the scientific literature that we have. Or if you're talking about React, obviously you're talking about a JavaScript library. And we don't really know in advance what's inside somebody else's head. So there's a lot of contextual problems. So that's where we're using Jupyter. And rather than spending millions of dollars, no offense to Luke Bielwald, rather than spending tens of millions of dollars on CrowdFlower, we didn't really have that available, so we started to use open source instead. And the idea is that Jupyter Notebooks are used for managing machine learning pipelines that perform the disambiguation. After we've used AI services to get transcripts and whatnot, after we get text together and we parse it and we start doing a lot of magic in terms of machine learning for building up indexes, et cetera, we still have to disambiguate. And so what we do is to use the notebooks as a way of getting the people and the machines to collaborate together. So a notebook serves as almost kind of a structured log. It's one part configuration file, one part data sample, one part log, and one part data visualization tool. And the nice thing about it is that for the most part, this is running at scale on, like I say, millions of elements in terms of chapters. It's running at scale, mostly automated. But if there's a problem, then a person can jump in and review what's going on with that pipeline by using Jupyter. And so sort of the statefulness of the pipeline is represented by Jupyter Notebooks. The other thing that's important is that machine learning here is not based on feature engineering or model parameter selection. The machine learning here is based on having people working with learning content people on my team, actually, so Taylor and Esty and myself, providing examples. Here's a chapter that is an example of JavaScript React. Here's an example of how to conduct an interview React. Here's an example of React that's none of the above. And so learning by example, providing exemplars, is a really powerful tool for us. And it's something that really enables the active learning to be practical. So the way that this works is that experts use notebooks to provide examples of chapters or video segments anywhere that there's a key phrase which has overlapping contexts. And then the machines build up ensemble models based on those examples. The model evaluation is all serialized out to the notebooks for later review if needed. The machines attempt to do annotation working at scale, so millions of pieces of content. And again, the same thing here. Are they talking about Golang? Are they talking about AlphaGo? Or are they using the verb go for something mundane? And this runs mostly automated. We're using Spark with scikit-learn to do a lot of the task management at scale, so we can run it in parallel. When the ensembles disagree, then the decision goes back to the humans to make a judgment call and provide further examples. Basically adds more examples to the notebooks. And then that goes back into training the models to be better. So it looks a bit like this, just the way that we're using things. We use SSH Tunnels from our server environment where we're running machine learning. We have some beefy machines to do that. We use an SSH tunnel so a person who's working with it, the expert, can run Jupyter in their browser. And I guess another way of looking at this is that both the machines and the people become collaborators on shared documents. So in a lot of ways, this is anticipating what will be coming up with Jupyter, Jupyter Lab, using Google Drive for shared documents, essentially. The machines are writing part of the docs. There's an open source project. It's called NB Transom. It's tiny. It's not a lot of code. It's based on top of NB format and pandas. And the idea is being able to leverage a notebook as partly as a data store, partly as like the analytics view for this. One thing that we did do was to come up with a custom pretty printer for it, just so we could kind of optimize its interaction with Get. We don't want to dump out a lot of data and then have it all be on one line. It's kind of a small nit, but it's actually helpful to tune your pretty printers for what goes into the notebooks. Now, in terms of machine learning, is everybody here familiar with something called the no free lunch theorem? The idea is there's going to be bias, and you're going to have to tilt your operations one way or another. So for us, it's better to err on the side of less false positives, more false negatives, because we want to give people good search results. We don't want to give them bad search results. We have a lot of content. If we miss recall, if we miss showing absolutely everything that would be possibly good to show, and instead show a lot of things that are good to show, it's still going to overwhelm what people can look within a search page. Now, in terms of active learning, that's a policy that's typically called bias toward exemplars, most likely to influence a classifier. So we're trying to select for things that are going to help the classifier more. So examples of this, like we've found, we don't use the introductory chapters in our examples. Those are just, they're all over the map. So we make sure to sort of start with chapter 2. We know that we shouldn't use a bibliography or an appendix or things like that too. So we've been trying to develop some policy as we go along, and we're doing this, and we share this a lot of what seems to work or what doesn't. And potentially, even though right now there's 3 of us at OReilly who are being the experts to this, potentially it wouldn't be hard to put into the search UI and allow customer service people to do it instead. They're the ones who are talking with customers. They hear when there's bad content being recommended, and they should be the ones who can push a button and show good examples versus bad examples. So this is our view of human in the loop as a management strategy, that really this should extend out to something like a customer service organization, possibly to a sales organization, et cetera. Okay, and then, so summary, a little more deep learning. This is our Tarsier, sort of our mascot, but I wanted to run it through deep learning. So, and I know that Edie Friedman's going to kill me for this. My personal op-ed is that the game that we're working with isn't about replacing people by using AI. Rather, it's augmenting what people do. I was talking earlier when we used the illustration. We do 20 of these conferences a year. And with 20 conferences a year, some of them are much larger. Strata here will have thousands of people. That's enough video that if we had an editor, a development editor, review all of our video, they would have to have their finger on the fast forward button for 10 months out of the year. I mean, that's the data rate. And there's no way the editors are going to do that. So instead, can we use AI tooling, which is available, to produce summaries? So this is the game that we're getting into now, is can we take 40-minute talk and summarize it on a page and show some of the structure, what are the main things that are being, the main phrases, the main key terms, et cetera, that are being used, and then allow an editor to go from that text to a minute-second time code inside the video. That's useful for editors to make their life more livable. It's useful also for customers, too. And the other thing that's coming up is, YouTube was introduced 12 years ago. My kids are 13 and 12, and they live in YouTube. And as a media company, we're pretty good at this, and we're just now sort of wrapping our heads around how to work with video. And we've been doing it for a while, but not a long while. And we're still learning what's effective or not. And so we're still sort of coming up to speed on video, even though the demand for video is really outpacing the demand for books. But the worry that I have is that I went to, anybody been to a drone race? So I got invited to go to the first legal drone race in California recently, because there's been a lot of illegal ones too. They're pretty cool. And so we went to one, and I don't know, it was Xfinity was sponsoring it. They dropped way too much money. But it was a lot of fun. But the thing is, the drone race is it's inside of a warehouse, and it's all built on augmented reality. So the drone racetrack is an AR setup. And so all the pylons that they're flying through are all based off of AR. And then the pilots are working in first-person view in VR. So both the pilots and the audience, if you want, you can put on a goggle and watch the race, from a given competitor's perspective. And so that's one compelling thing about drone races is it's very much this AR, VR kind of a thing. We're seeing where in manufacturing, we see in industrial use cases where people are being trained using AR. We're certainly seeing that in areas of military. That's been going on for a long time. For what it's worth, I went to West Point way too many years ago. And my colleagues who are still around that kind of space, they train their troops using large VR systems a lot. Gosh, we had to crawl through mud. So even though we're still now just sort of catching up to video, the concern I have is that the next generation of learning materials that's coming up is going to be based off of AR and a lot more embedded kinds of applications like this. And the data rates on that will be much higher. So that's what we're trying to go for. So we're not replacing people. We're trying to make this kind of work much more livable. And now this is just my opinion. It doesn't reflect the opinions of my employer. But the opinions of my employer are that we'll never run out of jobs. There's a great video on this. But the idea is that we're not going to run out of jobs until we run out of problems. And so we don't really look at AI as replacing people. And in fact, in some ways, it may actually be causing more jobs for us. So a lot of shout-outs to folks who've helped out on this. And if you want it, we've got a lot more material about this at Strata and AI conference. And if you want to get a hold of me, Twitter is usually a pretty good place to catch me. And I think I'm running out of time, so I'll catch some questions in the back. But thank you very much. Already, we have a few minutes to do some questions? Okay, great. Any questions? Yes.
Maybe a philosophical question. It's regarding augmented experts. How do we become experts? Maybe using a lot of simple pieces until we will be experts.
Yeah. No, it's a great question. I mean, from our perspective, we're continually seeing technologies or other things. We work in design, we work in business, we work in DevOps, we work in machine learning. And we're continuing seeing technology stacks evolve and learning curves accelerate, and new experts emerge. And I mean, a lot of it is somebody has a hard problem and they work very hard to articulate a solution and they keep going after it, but then they also are able to show enough leadership to get other people involved. So I think that the answer to that goes back to what Wes McKinney gave in the keynote this morning, and also what Peter Wang was talking about in their respective keynotes, about just putting the code on GitHub doesn't mean you have a successful open source project. It's more about building a community and getting involved in that community. And so that's a lot of where we see the experts emerging, is by being engaged in these communities to solve problems that a lot of other people have. It could be just that you're in a company and you have to solve a problem, and it's a hard problem, and you do it right, you get lucky, and then other people start using it. But I think it's more about the community aspects, the leadership, the socialization of the problem. Does that help answer it? Or you do a PhD on it and nobody else does. And like Luke Bielwald, you do that, and then you launch a company, and then 10 years later it becomes successful. Okay, sorry.
Since you're using ontologies, I'm curious about what technology you're using for triple stores and Sparkle engines.
Excellent question. So I definitely lived through 2005 and what happened with semantic web. And there are a lot of great things back there. And the lesson that I learned after watching Radar Networks and others, the short answer is we don't touch Sparkle with a 10-foot pole. And we have absolutely no triple stores. Not to disparage them, but what we've learned, we do use, our representation is based off of OWL, because we use SCAs as the simple knowledge ontology. We use SCAs as kind of the backbone, and that ties into Library of Congress, and of course it ties into DBpedia and others that we need. So OWL and SCAs very handy. For representation, we're using N3 Turtle, so TTL as a representation. And then in Python, we use RDFlib. And so that really buys us a lot. By using RDFlib, we can do a lot of manipulation, we can do validation, et cetera.
So you have small ontologies.
Pardon?
You have small ontologies.
Well, the curated part is on the order of hundreds of rules. Not hundreds of triples, but hundreds of rules. Or hundreds of subject-object nouns. But then the trick that we do is usually using NetworkX. So we can take our main ontology and then reify it, add in other parts. But even then, we're still working with a graph that we can run in memory with NetworkX. So that's what I would recommend, is like, don't go to a triple store, just use NetworkX, if you can get away with it. I used to work on Spark and GraphX, and I'm a big fan of Titan and others. So there's a lot of great graph databases these days. Other questions? If not, I'll be around, and I should probably make room for the next person. Thank you very much.
All right, great. Thank you, Paco.